Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The Amazon rainforest, Earth's largest tropical wilderness, is dying of thirst. As we venture into 2025, satellite images reveal a troubling transformation. Rivers that once carved through dense jungle now resemble dusty veins in a withering leaf. This isn't merely a temporary dry spell. It's part of an accelerating pattern that scientists have tracked with growing alarm over the past decade. The Amazon basin spans over 2.7 million square miles across 9 nations, containing approximately 10% of the world's known biodiversity and storing billions of tons of carbon dioxide. For centuries, this vast ecosystem has regulated global weather patterns, earned its nickname as Earth's lungs by producing 20% of our planet's oxygen, and served as home to over 30 million people, including hundreds of indigenous groups with irreplaceable cultural knowledge. But today, this crucial planetary life support system faces an unprecedented threat. In 2023 and 2024, severe drought conditions reached historic levels, with major waterways, like the Rio Negro, dropping to their lowest recorded levels in over a century of monitoring. In Manaus, Brazil, the region's largest city, water levels fell more than 30 feet below normal, stranding communities that rely on river transport for basic necessities. Dr. Elena Martinez from the Earth Systems Research Laboratory explains, "What we're witnessing isn't just an anomaly. It's consistent with climate models that predicted intensifying drought cycles in the Amazon as global temperatures rise. The system is approaching a tipping point where the forest's internal moisture recycling mechanisms begin to fail. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together." The science behind this crisis reveals a complex interplay of natural and human-induced factors. The Amazon traditionally creates much of its own rainfall through a process called evapotranspiration. Trees release water vapor through their leaves, which forms clouds and returns as rain. This self-sustaining hydrological cycle has maintained the rainforest for millennia. Climate records show that the Amazon typically experiences periodic droughts linked to El Niño events and Atlantic Ocean temperature fluctuations. However, what distinguishes recent droughts is their increased frequency, duration, and severity. Since 2005, the region has experienced 5 major drought events. In 2005, 2010, 2015-16, 2020, and 2023 through 2024, compared to only 2 such events in the entire 20th century. According to research published in the journal Nature Climate Change, these intensifying droughts correlate strongly with rising global temperatures. For every 1 degree Celsius increase in global average temperature, moisture evaporation rates increase by approximately 7%, placing additional stress on ecosystems worldwide. Dr. Carlos Nobre, one of Brazil's leading climate scientists, has been monitoring these changes for decades. His research indicates that the combination of climate change, deforestation, and agricultural expansion is creating a dangerous feedback loop. As trees are removed and temperatures rise, the forest loses its ability to generate rain. This creates drier conditions, making remaining trees more vulnerable to drought, fire, and further human encroachment. The data is sobering. Satellite monitoring from the European Space Agency's Sentinel mission shows that ground moisture content across the central Amazon fell by 28% between 2015 and 2024. River flow measurements taken at 60 monitoring stations throughout the basin indicate that average water volumes have decreased by nearly 15% over the same period. As our planet continues warming, scientists predict these trends will accelerate, potentially transforming large portions of this ancient rainforest into savanna. The implications extend far beyond the region itself. They reach into the planetary systems that sustain life as we know it. Understanding the Amazon's drought requires looking at both atmospheric physics and the biology of rainforest ecosystems. At its most fundamental level, the crisis stems from a disruption in the region's hydrological cycle, a complex system that has evolved over millions of years to create one of Earth's most water-rich environments. The Amazon basin typically receives between 2,000 and 3,000 millimeters of rainfall annually. This abundant precipitation has historically been maintained through a remarkable natural mechanism. The rainforest generates approximately half of its own rainfall. As moisture evaporates from the Atlantic Ocean and moves inland across the continent, it falls as rain, is absorbed by plants and then released back into the atmosphere through transpiration, a process where water vapor escapes through tiny pores in leaves called stomata. This recycled moisture forms clouds that precipitate again, further inland, creating a cascade effect that carries humidity thousands of miles from the coast to the Andean foothills. Dr. Antonio Donato Nobre from Brazil's National Institute for Space Research describes it as flying rivers, aerial corridors carrying more water than the Amazon River itself. The rainforest functions as a vast biological pump, explains Dr. Sarah Chen, atmospheric scientist at the University of California. Each large tree can release up to 1,000 liters of water vapor daily. Multiply that by the billions of trees in the Amazon, and you have an atmospheric moisture engine of planetary significance. This delicate system is now failing. Climate measurements show that average temperatures in the Amazon have increased by 1.1 degrees Celsius since 1970, exceeding the global average. This warming accelerates evaporation from soil and water bodies, while simultaneously stressing the forest's capacity to maintain healthy transpiration rates. When trees experience prolonged water scarcity, they protect themselves by closing their stomata, reducing water loss but also decreasing humidity contribution to the atmosphere. Satellite data from NASA's GRACE mission, which measures changes in Earth's gravitational field affected by water distribution, indicates the Amazon basin lost approximately 300 cubic kilometers of water storage between 2019 and 2024, equivalent to the volume of Lake Michigan. Adding to these climate pressures, deforestation has removed approximately 18% of the original forest cover since 1970. Every hectare cleared represents thousands of trees no longer participating in the moisture cycle. Research published in Proceedings of the National Academy of Sciences demonstrates that deforested areas experience temperature increases up to 4 degrees Celsius higher than neighboring forested regions, creating hotspots that disrupt local rainfall patterns. The forest's eastern and southern edges, particularly in Brazil's arc of deforestation, now receive 35% less rainfall than historical averages. These regions show the earliest signs of what scientists call savannization, the gradual transformation of rainforest into drier, less biodiverse grassland ecosystems with scattered drought-resistant trees. Compounding these problems, increasing frequency of wildfires releases enormous quantities of carbon dioxide while destroying canopy cover, critical for shading and moisture retention. In 2023 alone, fire detection systems recorded over 130,000 fire outbreaks in the Amazon region, the highest number since 2010. Dr. Paulo Moutinho from the Amazon Environmental Research Institute notes, "We've created a dangerous feedback loop. Drought makes the forest vulnerable to fire. Fire creates more open, drier conditions. These conditions invite human activities like agriculture that further remove forest cover. And all these factors together intensify subsequent droughts. Climate models examining these interactions reveal a troubling threshold. If deforestation exceeds 25% of the original forest area, just 7% more than current levels, and global temperatures continue rising at present rates, large portions of the Amazon could pass a critical tipping point where the system's internal moisture recycling collapses entirely." What makes this situation particularly alarming is the discovery that drought effects appear non-linear. Small, incremental changes can suddenly trigger disproportionate responses once certain thresholds are crossed, much like how water remains liquid until precisely 0 degrees Celsius, when it abruptly transforms into ice. The Amazon drought isn't merely affecting trees, it's triggering a cascade of ecological consequences. throughout the world's most biodiverse ecosystem. As water becomes scarce, a complex network of interdependencies begins to unravel, revealing vulnerabilities that scientists are racing to understand. In healthy rainforest systems, trees access deep groundwater during dry periods, maintaining critical ecosystem functions. However, prolonged drought exhausts these reserves, forcing even well-established trees into physiological stress. When internal water pressure drops below critical thresholds, air bubbles form in their vascular systems, a phenomenon called cavitation, essentially creating an embolism that can kill even centuries-old giants. What we're witnessing is the selective culling of species based on drought tolerance, explains Dr. Luciana Vanni of the Tropical Forest Research Institute. Trees with shallow root systems or less efficient water conservation strategies are dying first, altering forest composition in ways that further reduce moisture retention. Recent field surveys across 60 monitoring plots reveal mortality rates among certain tree species have increased by over 70% during extreme drought years. More troubling still, data shows that fast-growing pioneer species, which typically help forests recover from disturbances, are among the most vulnerable to extended dry periods. This botanical disruption reverberates through animal communities. Frugivorous species, animals dependent on fruit, face particular challenges as drought reduces flowering and fruit production. Monitoring programs tracking spider monkey populations in central Amazonia documented a 38% decline in fruit availability during the 2023 drought, corresponding with expanded foraging ranges and declining birth rates among these keystone seed dispersers. The drought's impact extends below the forest floor. Soil microbial communities, the invisible ecosystem engineers that cycle nutrients and maintain soil health, show dramatic compositional shifts under drought conditions. Metagenomic analyses from drought-affected areas reveal decreases in beneficial fungal networks like mycorrhizae, which help plants access water and nutrients. These microscopic changes carry macroscopic consequences, reducing the forest's resilience to future stresses. Aquatic ecosystems face perhaps the most immediate threat. As rivers and floodplains shrink, aquatic species become concentrated in ever-diminishing water bodies with rising temperatures and declining oxygen levels. In 2024, researchers documented mass fish die-offs in over 20 major tributaries of the Amazon River, with mortality estimates exceeding 2 million individual fish. The Amazon's aquatic and terrestrial ecosystems aren't separate entities. They're deeply interconnected, notes Dr. Miguel Pereira, aquatic ecologist at the Federal University of Amazonas. Fish provide essential nutrient transport between river channels and floodplains, while flooded forests serve as critical nursery habitats. When this hydrological connection breaks down, both systems suffer. Indigenous communities, whose knowledge spans countless generations, report unprecedented changes. Teresa Yapuma, elder from the Matses people, describes phenomena never before recorded in their oral histories. The forest speaks through patterns, when certain flowers bloom, when frogs call, when fish migrate. Now these patterns are broken. Animals appear where they shouldn't be. Fruiting seasons come at wrong times, the rhythm is lost. These disruptions resonate through trophic levels. Apex predators like jaguars, facing prey scarcity in drought-affected areas, increasingly venture into human settlements. Meanwhile, disease vectors such as Anopheles mosquitoes concentrate around remaining water sources, creating potential hotspots for malaria transmission. Scientific monitoring programs have also detected subtle yet troubling shifts in carbon dynamics. The Amazon historically functioned as a carbon sink, absorbing more carbon dioxide than it released. However, measurements from eddy covariance towers, sophisticated instruments that track carbon exchange between ecosystems and the atmosphere, indicate that severely drought-stressed regions have become net carbon sources during extreme dry periods. Dr. Thomas Lovejoy, who pioneered the long-running biological dynamics of forest fragments project, summarizes these interconnected crises. The Amazon isn't just experiencing ecological change, it's undergoing ecological reorganization. The system is being fundamentally restructured, in response to new climatic realities, with certain thresholds already crossed and others looming dangerously close. What emerges from this scientific accounting is a portrait of ecosystem domino effects, each fallen piece accelerating the collapse of others in a self-reinforcing cycle that becomes increasingly difficult to reverse. The Amazon drought's human impact transcends statistics, revealing profound connections between environmental and social vulnerabilities. For the 35 million people who call the Amazon basin home, including over 350 indigenous groups, changing rainfall patterns represent an existential threat to centuries-old ways of life. In riverside communities known as ribeirinhos, traditional livelihoods depend on predictable flood pulses that fertilize floodplain agriculture and regulate fish movements. Edson Carvalho, fisherman from Carreiro da Várzea in Brazil, describes the new reality. In my father's time, we knew exactly when fish would spawn, when to plant, when high water would come. Now, the river betrays us. Last year, our community was stranded for 3 months when the water dropped too low for boats, our only connection to medical care and markets. Health impacts appear increasingly severe. Hospital admission data from 300 clinics across the Brazilian Amazon shows a 42% increase in respiratory illnesses during drought periods, driven by wildfire smoke and elevated dust levels. Waterborne disease outbreaks have surged by 70% in communities forced to rely on stagnant water sources as wells and streams run dry. For indigenous peoples, the drought threatens not just physical health, but cultural survival. These communities possess irreplaceable ecological knowledge developed over thousands of years, including sophisticated understanding of plant properties, wildlife behavior, and sustainable resource management. As traditional food and medicinal plants become scarce, this living heritage faces erosion. Our calendar, our ceremonies, our stories, all connected to seasonal patterns that no longer exist, explains Paulo Mutumbajoy, elder from the Inga people. Young people question the validity of traditional knowledge when predictions fail. But this knowledge isn't wrong, it's the climate that has changed. Economic consequences ripple outward from the forest. Agricultural projections estimate $24 billion in losses across Brazil, Bolivia, Peru, and Colombia between 2020 and 2025 due to drought-related crop failures and livestock deaths. In Brazil's Mato Grosso, state soybean yields declined by 31% during the 2023 growing season, affecting global commodity prices. Hydroelectric power, supplying over 60% of the region's electricity, faces unprecedented challenges. The Belo Monte Dam complex, one of the world's largest, operated at just 43% capacity during recent drought months, triggering energy rationing in major Brazilian cities and cascading effects through industrial sectors. Urban centers within the Amazon aren't immune. Manaus, a city of over 2 million people, experienced water rationing affecting 70% of neighborhoods during peak drought, while water quality deteriorated due to increased concentration of pollutants in depleted rivers. Similar situations have emerged in Belém, Iquitos, Leticia, and other Amazonian cities. Dr. Maria José Andrade, from the Observatory of Human Rights and Climate documents another troubling pattern: climate migration. We're tracking population movements that correlate directly with drought severity. When communities can no longer sustain agriculture or fishing, people move, first to regional centers, then to major cities, creating new informal settlements, often lacking basic infrastructure. These migrations intensify existing socio-economic pressures. Housing shortages in Manaus increased by 27% between 2022 and 2024, while unemployment among climate-displaced persons exceeds 40%, nearly double the regional average. Government response capabilities vary dramatically across the 9 countries sharing the Amazon basin. While Brazil's Disaster Management Agency mobilized emergency water deliveries to 450 communities during recent droughts, many remote areas in Peru, Colombia, and Bolivia received minimal support due to logistical challenges and limited resources. International aid has increased, with the United Nations allocating $112 million for humanitarian response between 2022 and 2024. However, long-term adaptation funding remains insufficient, covering less than 15% of identified needs for infrastructure improvements and livelihood diversification programs. Dr. Roberto Sanchez of the Pan-Amazonian Social Research Network emphasizes that vulnerability isn't distributed equally. Communities with secure land rights, diversified economic activities, and strong social organization demonstrate greater resilience. The most severe impacts concentrate where historical marginalization meets environmental change. As drought conditions intensify, scientists and policymakers increasingly recognize that environmental security and human security in the Amazon are inseparable. Climate adaptation strategies must address both ecological restoration and community resilience to navigate what has become not just an environmental crisis, but a profound humanitarian challenge. The Amazon drought, while geographically centered in South America, generates far-reaching consequences that ripple through Earth's interconnected systems. These effects, atmospheric, climatic, economic, and biological, demonstrate how ecological disruption in one region can trigger global chain reactions. Atmospheric scientists have identified the Amazon as a crucial component in global circulation patterns. The forest's immense evapotranspiration creates what meteorologists call flying rivers, aerial moisture corridors that transport water vapor across continents. Research from Columbia University's Earth Institute demonstrates that approximately 20% of rainfall in South America's agricultural heartland originates from Amazon moisture. We've detected precipitation anomalies as far south as northern Argentina that correlate directly with Amazon drought conditions, explains Dr. Javier Morales of the International Research Institute for Climate and Society. Agricultural regions in Paraguay, Bolivia, and southern Brazil have experienced rainfall decreases of 25 to 30% during periods of severe Amazon drought. These alterations to moisture transport pathways affect more distant regions through atmospheric teleconnections, statistical relationships between weather events separated by large distances. Computer models suggest that reduced Amazonian evapotranspiration weakens certain jet stream components, potentially contributing to rainfall pattern changes across North America and increased precipitation variability in Western Europe. Carbon cycle disruptions represent another global concern. The Amazon historically sequestered between 1 and 2 billion tons of carbon dioxide annually, approximately 5% of human emissions. However, during severe drought years, portions of the forest become carbon sources rather than sinks. Atmospheric monitoring stations have measured carbon dioxide releases exceeding 500 million tons during extreme drought events, effectively cancelling a significant fraction of the forest's typical climate mitigation service. Dr. Himanshu Patel, carbon cycle specialist at the Global Climate Observatory, explains, "The Amazon operates as Earth's green lung not just by producing oxygen, but by removing carbon dioxide from the atmosphere. As drought compromises this function, it accelerates global warming, creating a dangerous feedback loop. Economic ripples extend worldwide through commodity markets and supply chains. The Amazon region produces significant percentages of global soy, beef, coffee, cacao, Brazil nuts, and numerous pharmaceutical compounds. Production disruptions translate to price volatility in these markets. In 2024, global coffee prices increased by 38%, following drought-related harvest failures in Brazil's Amazonian coffee regions. For pharmaceutical industries, the stakes involve both existing medicines and undiscovered compounds. Over 25% of modern drugs originated from rainforest plants, yet scientists estimate only a small fraction of the Amazon's pharmacological potential has been investigated. Each species lost potentially eliminates valuable biomedical resources, an economic and public health consequence difficult to quantify but increasingly recognized in bioprospecting valuations. Biodiversity impacts extend beyond the region through migratory species. The Amazon hosts over 1,000 bird species, many migrating annually between South America and North America. Drought-related habitat degradation affects breeding success and population dynamics across hemispheres. Monitoring data shows that 17 migratory species that overwinter in the Amazon have experienced population declines exceeding 30% since 2010. Perhaps most concerning are potential tipping points in Earth system stability. The concept of planetary boundaries, thresholds beyond which Earth systems may shift into new states, includes biosphere integrity and climate change as critical parameters. Amazon degradation pushes against both boundaries simultaneously. Research, published in Science Advances, suggests that Amazon drought conditions increase risks of abrupt ecosystem shifts not just locally but in connected systems. Computer simulations indicate that loss of Amazon moisture recycling could affect monsoon dynamics in Asia, potentially altering rainfall patterns for billions of people across India, Bangladesh, and Southeast Asia. Disease ecology provides another, global connection. The Amazon hosts enormous viral and bacterial diversity, mostly circulating harmlessly within wildlife populations. However, drought forces unusual wildlife movements and increases human-animal contact as both species concentrate around remaining water sources. Epidemiologists have documented increased incidence of zoonotic diseases, pathogens jumping from animals to humans, during severe drought periods. Dr. Elena Martinelli from the Planetary Health Alliance notes, ecosystem disruption changes disease, transmission dynamics in ways we're just beginning to understand. The combination of biodiversity loss, changing wildlife behavior, and increased human vulnerability creates conditions where novel pathogen spillover becomes more likely. Ultimately, the Amazon drought illustrates the concept of planetary connectedness, that Earth operates as an integrated system, where regional changes generate global consequences. As humanity navigates an increasingly unstable climate, understanding these cross-scale linkages becomes essential for effective response strategies that acknowledge both local impacts and global reverberations. In the race to understand and address the Amazon drought, cutting-edge technologies are transforming how scientists monitor, model, and potentially mitigate this unfolding crisis. These innovations span disciplines from remote sensing to artificial intelligence, offering unprecedented insights into ecosystem dynamics, while suggesting potential intervention pathways. Satellite monitoring represents the first tier of technological response. Beyond traditional optical imagery, the European Space Agency's Sentinel-1 mission employs synthetic aperture radar, SAR, that penetrates cloud cover, a critical advantage in the perpetually cloudy Amazon. These systems measure soil moisture to depths of 5 centimeters, tracking drought progression with weekly resolution across the entire 2.7 million square mile basin. NASA's GRACE follow-on mission, launched in 2018, detects minute changes in Earth's gravitational field caused by water mass redistribution. GRACE allows us to quantify groundwater depletion invisible to the naked eye, explains Dr. Helena Rodriguez, hydrologist at the South American Earth System Science Center. We've measured groundwater losses exceeding 50 cubic kilometers per year in the central Amazon, water stores that took centuries to accumulate. Emerging hyperspectral satellite capabilities add another dimension by detecting precise light wavelength patterns reflected from vegetation. These spectral signatures reveal plant physiological stress before visible symptoms appear. The recently deployed NASA Surface Biology and Geology satellite can identify drought-stressed trees up to 3 months before they show physical signs of decline, creating early warning systems for forest dieback. On the ground, sensor networks provide real-time data streams. The Amazon Tall Tower Observatory, a 325-meter research platform in central Amazonia, houses instruments measuring thousands of atmospheric and ecological parameters. Complementing this, researchers have deployed networks of low-cost solar-powered IoT Internet of Things sensors throughout remote areas, transmitting microclimate data via satellite uplinks. We've essentially created a nervous system for the forest, describes Dr. Marcos Silveira, instrumentation specialist at Brazil's National Institute for Amazonian Research. 10 years ago, we had maybe a dozen monitoring stations across the entire Amazon. Today, our network includes over 8,000 distributed sensor nodes, providing unprecedented spatial resolution. These massive data streams require advanced analytical approaches. Artificial intelligence systems now integrate satellite imagery, ground sensors, and climate models to create remarkably precise drought forecasts. Machine learning algorithms trained on decades of historical data can predict drought development, up to 9 months in advance with 70% accuracy, allowing for proactive resource allocation and emergency planning. Digital twin technology, creating virtual replicas of physical systems, has emerged as a powerful modeling tool. The Amazon Digital Twin project combines multispectral imaging, LiDAR topography, and ecological surveys to construct a comprehensive three-dimensional virtual model of forest dynamics. This platform enables scientists to simulate potential interventions and policy scenarios, testing outcomes before implementing them in the real world. Biotechnology offers another frontier for drought response. Researchers have identified naturally drought-resistant tree varieties by studying survival patterns in extremely dry regions of the Amazon. Using advanced genomic techniques, they've isolated specific genetic markers associated with water stress, tolerance. These discoveries inform selective breeding programs and potential genetic conservation initiatives for vulnerable species. Reforestation technology has evolved significantly. Drone-based seeding systems can now plant up to 100,000 trees daily in remote or difficult terrain. These drones identify optimal planting locations using AI terrain analysis, then fire specially designed seed capsules containing nutrients, moisture-retaining hydrogels, and beneficial microbes that improve seedling survival rates in drought conditions. Water management technologies show particular promise for communities. Atmospheric water harvesting systems, devices that extract moisture directly from humid air, have been deployed in 60 indigenous villages facing critical water shortages. These systems generate up to 500 liters of clean water daily, using only solar power, providing emergency supply during extreme drought. For agricultural adaptation, precision irrigation controlled by soil moisture sensors reduces water consumption by up to 60% compared to traditional methods. These systems have been implemented in over 3,000 small-scale farms throughout the Amazon's agricultural frontier, demonstrating that technological solutions can be both sophisticated and accessible. Perhaps most ambitious are emerging climate intervention proposals. While controversial, research into biomimicry-inspired atmospheric moisture recycling systems seeks to artificially enhance the forest's natural rain-generating capacity. Prototype systems use solar-powered condensers and evaporators to accelerate water cycling in strategic locations, potentially reinforcing weakened hydrological processes. Dr. Carlos Mendes, from the Institute for Advanced Amazonian Studies, offers perspective on these technological frontiers. Technology alone cannot solve the Amazon drought crisis. Policy, economics, and human behavior remain fundamental. However, these innovations dramatically improve our understanding while expanding our response options. The challenge lies in deploying these capabilities equitably and ethically across the diverse social landscape of the Amazon. As the Amazon drought intensifies, the scientific community has moved beyond merely documenting decline toward identifying concrete pathways for intervention and adaptation. These emerging strategies span multiple scales, from local community actions to international policy frameworks, creating a blueprint for preserving the rainforest's vital functions while supporting human communities through unprecedented transitions. Restoration ecology represents the front line of direct intervention. Traditional reforestation approaches have evolved into sophisticated ecosystem reconstruction methodologies that consider forest complexity beyond simply planting trees. The Trans-Amazonian Restoration Corridor, launched in 2022, employs advanced nucleation techniques, establishing small, diverse plant assemblages that naturally expand outward. To reconnect fragmented forest areas, across 600 kilometers of previously deforested land. We're not just replacing trees, we're reinstating ecological processes, explains Dr. Isabella Ferreira, lead scientist for the project. By strategically selecting pioneer species that enhance soil moisture retention and prioritizing planting along watershed boundaries, we're re-establishing hydrological functions fundamental to drought resilience. Early results demonstrate promise. Areas employing these targeted restoration approaches show microclimate improvements within 3 years, including temperature reductions of up to 3.5 degrees Celsius and relative humidity increases of 22% compared to unrestored control sites. Water management innovations focus on slowing the hydrological cycle, allowing precipitation to recharge groundwater rather than rapidly flowing out of the system. Simple technologies like contour trenches, infiltration ponds, and check dams have been implemented by over 800 communities across the Amazon basin, effectively functioning as water retention landscapes that maintain moisture during dry periods. Indigenous knowledge systems offer critical guidance for these efforts. The Kayapo people's traditional management techniques, involving strategic controlled burns early in the dry season and maintaining diverse forest gardens, have demonstrated remarkable drought resilience. Scientific validation of these approaches has led to their incorporation into Brazil's National Adaptation Plan and similar frameworks in neighboring countries. Policy innovations increasingly recognize that preserving the Amazon requires economic transformation. Payment for ecosystem services programs, where downstream beneficiaries compensate upstream forest stewards, have expanded dramatically. Colombia's Water Fund initiative now generates over $60 million annually for watershed protection, while Peru's National Forest Conservation Program compensates indigenous communities for maintaining forest cover based on carbon storage, biodiversity, and hydrological services. International finance mechanisms have evolved to address underlying economic pressures. The Amazon Climate Finance Initiative, launched in 2023 with $12 billion in initial capitalization, provides low-interest transition financing for agricultural operations shifting to sustainable practices. The program's innovative productivity not expansion approach has helped over 22,000 farmers increase yields on existing agricultural land while preserving remaining forest. Science policy interfaces have strengthened through initiatives like the Amazon Science Panel, an independent body of researchers providing direct scientific guidance to policymakers across all 9 Amazonian nations. This panel delivers quarterly drought assessment reports that inform regional emergency response, while maintaining a continuously updated dashboard of environmental indicators accessible to both governments and civil society. Education and communication. Strategies recognize that human behavior and perception form the foundation for lasting change. The One Amazon curriculum, implemented in schools across the region, combines scientific literacy with traditional ecological knowledge, reaching over 4 million students annually. Complementing this, community-based monitoring networks empower local populations to participate directly in scientific data collection, strengthening both the information base and social investment in solutions. Dr. Valentina Campos, social ecologist at the University of the Amazon, emphasizes the importance of this participatory approach. Technical solutions imposed without community engagement invariably fail. The most successful drought adaptation initiatives are those where scientific expertise and local knowledge develop solutions together, recognizing that resilience emerges from social structures as much as ecological ones. Looking forward, scenario planning exercises conducted by multinational research teams outline 3 potential trajectories for the Amazon through 2050: continued degradation, stabilization at a lower functioning state, or regenerative recovery. Their findings suggest the region stands at a decisive crossroads, with actions taken in the next decade likely determining which path unfolds. The scientific consensus emphasizes that while the Amazon drought presents profound challenges, fatalism is unwarranted. Dr. Robert Zhang from the Earth Systems Resilience Center concludes, the rainforest has survived climate fluctuations throughout its evolutionary history. What's unprecedented now is the rate of change and the combination of stressors. Yet our research clearly demonstrates that targeted interventions can meaningfully increase resilience even under pessimistic climate scenarios. This emerging synthesis, combining cutting-edge science, traditional knowledge, economic innovation, and social engagement, offers a template not just for addressing the Amazon crisis, but for navigating the broader climate challenges facing humanity. As the planet's largest rainforest struggles to maintain its life-giving cycles, the response to this crisis may well determine whether we can successfully adapt to a rapidly changing Earth system. In the Amazon struggle, we glimpse both our vulnerability and our capacity for transformative action, a microcosm of the greater climate challenge that will define the coming decades.